This conference will now be recorded.
Okay. Good morning, everyone. Let us start with this session. In today's session, will be taking an overview of the challenges and opportunities in VLSI design. Uh, this would help you understand the VLSI design flow and also help you understand what exactly is the front end domain, what exactly is the back end domain, what are the opportunities, and what are the some of the challenges we face in the VLSI design flow. So this will be the agenda. Just give a minute. I need to take one presentation of this rather.
This conference will now be recorded.
So as I have mentioned, today we will be starting with the challenges and opportunities in the VLSI design flow. This will be the agenda. So first we will start off with understanding the basics of an electronic system, and we'll be talking about, as part of this we'll be understanding the difference between what exactly is VLSI and what is embedded system. What is the skill set that you require to become a VLSI engineer? What skill set do you require to become an embedded system engineer? And we will also talk about the VLSI design flow. As part of that, we'll talk about front end domain flow and back end domain flow. Then we'll talk about some of the challenges that we face in the VLSI design flow. Then we'll discuss about VLSI domain and different job roles and what is the skill set that is required for these job roles. Then we'll also understand how do you choose a right domain. Like, see, VLSI consists of different job roles. How do you choose the right domain among these different job roles? Then we'll also discuss about how to prepare for the job. Like, let's say you're pursuing third year BTech or fourth year you're pursuing MTech. So how do you prepare for the jobs? Then we'll also talk about why should you choose VLSI as a career option. Then I'll just go over some of your questions as well. So just a brief about my profile. My name is Srinivas Reddy, and I am the founder of VLSI Guru Institute. You can go, I mean, to get more about VLSI Guru Institute, you can go to our page vlsiguru.com. I have a dual degree BTech MTech from IIT Madras in 2005. I have passed out, and I have 11 plus years of professional training experience. This is my 12th year. I have started my VLSI teaching profile career from 2012, and I have around 14 plus years of working experience. Currently, I'm into full time into teaching, and I am also a lead trainer for Mentor Graphics higher education program. Uh, First, let's now get into the our today's session agenda. Let's start off with understanding the electronic systems. uh, what exactly is an electronic system? I mean, before we get into these slides, let's understand what makes up an electronic system. So if you think of an electronic system, it can be your laptop, it can be your mobile phone, or it could be a your desktop, or any kind of electronic system you take. Even you take an example of a washing machine. This is all that's also partly an electronic system. So what all things goes into an electronic system? If you see at very basic level, you have a hardware. On top of hardware, to control how hardware behaves, we have the drivers, also called as firmware. So firmware controls how the hardware is going to behave. On top of hardware, let's say this is the hardware. Above hardware you have firmware. Above firmware you have operating system. Then above operating system you have the applications, what we call as apps. So these are the different layers that are part of an electronic system. So if you have to repeat, so at the very basic level of a electronic system, you will find the hardware. On top of hardware you have the drivers, also called as firmware. And above firmware you have operating system, and above operating system you have different applications. Okay, with this basic understanding, let us now understand brief about electronic system. If you think of a mobile phone, what do you see in a mobile phone? Typically, if you open the mobile phone, you will see different components that make up the mobile phone. It could be the chips, the camera, it could be the USB related logic or the display related logic, different things that makes up the mobile phone. Now, what all things, let's understand what all things make up a mobile phone, or for that matter, an electronic system. See, at the very basic level, you have the hardware, which consists of different chips, processors, screen, USB port, camera, sensors, audio speaker, different things make up the hardware. Then there are things which we don't see. I mean, like the hardware is something we can see. Then there are things which we don't see. What are those things? Like it could be operating system, Android or iOS kind of operating system. Then you have firmware, like what we call as drivers. Okay, other than that, you have different applications. So how it works is, as I mentioned before, the different layers. What? Hardware. Above hardware you have drivers, also called as firmware. Above drivers you have operating system. Then above operating system you have applications. So how it works is the drivers interface with the hardware. So to understand this, we can take a simple analogy. Imagine a bus with passengers. I generally will take few real life analogies to make it easy for you to understand the things. So let's imagine we are sitting in a bus. Okay. Now, this system consists of three elements. You see, bus is there, then you have a driver, then you have the passengers. So the bus is like the hardware for us. Bus driver is like the firmware. Passengers are like operating system or applications. So in that case, how does it work? It is the driver who interfaces with the bus. Anything you want to control in the bus, it happens by driver controlling the bus. So he has few controls like the accelerator, the brake, clutch, gear, different things he controls, and he controls the bus. Now the passenger, if he wants to do something, let's say if he wants the bus to stop, he will not go and directly interface with the bus. He would rather give instructions to the driver, who in turn coordinates with, applies the required control in the bus to stop it or to accelerate, whatever. So the same way, applications talk to the operating system talks to the firmware talks to the hardware. So that is the hierarchy we discussed. Anything operating application wants to do, they will instruct it to the operating system. Operating system in turn give instructions to the driver. Driver in turn controls the hardware behavior. So this is applicable for any kind of electronic system. Now, if you look from a VLSI engineer perspective, so what is that VLSI engineer is responsible for? The VLSI engineer is responsible for development of the hardware. So it is the role of VLSI engineer, very large scale integration. VLSI engineer is responsible for manufacturing, for development of hardware. So embedded system engineer is responsible for development of firmware. Generally, the software engineer would be working on operating system. Software engineer responsible for development of OS. Now, as far the application is concerned, we can call even software engineer or app developers. There will be app developers for this, right? So these are the different categories of the people who work into this. Now, as a VLSI engineer, you are responsible for development of the hardware. You don't work with applications, you don't work with operating system, you don't even work with drivers. But since your immediate layer is hardware, see, as a hardware, what is your immediate upper layer? The driver. You need to know how the drivers will work. So a VLSI engineer should have a good understanding of hardware functionality, and also understanding of how firmware behaves. The firmware are nothing but drivers behave, interface with. Let's understand again. As a VLSI engineer, you should have a good understanding of the hardware functionality, also have understanding of the how firmware, that is the drivers, these drivers interface with the hardware, because this is the immediate layer with which you talk. You should know how this works. You should also know how the drivers will work. As a VLSI engineer, you don't bother about operating system, you don't bother about applications. Whereas, let us say I am an embedded system engineer, I would need to know how the hardware will work. I also need to know how to implement my drivers. I also need to know how operating system will talk to me. So three layers understanding I need to have. If I am an embedded system engineer, because I'm talking to hardware on one side, I'm talking to operating system on one side, I should have understanding of these three things. But not very in depth of hardware. I mean, how to develop hardware, I don't need to know. I only need to know how can I control. See, going back to the similar analogy, a driver doesn't need to know, a bus driver doesn't need to know how bus is manufactured. He only needs to know what are the controls. If I have to accelerate the bus, how should I do that? If I have to stop the bus, what should I do? If I want to change the gear, what should I do? If I have to change the mode of a bus travel, how should I do? That much understanding driver should have. Driver should don't need to know what metal is used, how it is manufactured, all those things he doesn't need to know. But someone who works on the development of bus, I mean making manufacturing of bus, need to have that complete understanding. That is the role of a VLSI. Now, has everyone understood the difference between a VLSI engineer and an embedded system engineer and a software engineer? Now, with this understanding, let us proceed further. Now, an electronic system, as I said, mobile phone has four layers. At the very basic level, you have hardware, which consists of processors, camera, and sensors, various things. I just listed few of them. Who develops the hardware? Can someone tell me who develops the hardware? It is the VLSI engineer who develops the hardware. Then, who develops the firmware or drivers? Do you understand the term why drivers is being used? Because it drives the hardware behavior. It controls the hardware behavior. Because it controls, it is called as firmware is called as a driver. Other than that, who develops the firmware? The person who develops the firmware is called as embedded system engineer. Then you have the third layer, what we call as operating system, which consists of Android OS, iOS, Windows, Linux. Who develops OS? It is the software engineer. Then finally, you have applications, the different apps that go into your mobile, laptop, or any electronic product. It could be GPay, WhatsApp, Maps, anything, right? Who develops applications? Mostly the software engineer or app developers. For an electronic device to work, all these four layers are essential. Let's say, going back to the bus example, can you have a can you have this thing working without having a driver? Without driver, can we is there any use of having bus and passengers? No, right? Now, without having the bus, without having hardware, can you do anything here? There is no use, right? See, for you to have a driver and passenger, you must have a bus. So that is why every layer is essential for an electronic system to work properly. You can't say that no need of firmware, no need of operating system. Everything has its own importance in the electronic system. Next, let us understand the VLSI design flow. uh, Now that we have understood an electronic system, now that we have understood what is the difference between a hardware, the firmware, and the software and the applications, we know that it is the VLSI engineer who is responsible for design and development of the hardware. So now let us try to understand what are the various steps involved in development of a hardware. So for that, let's understand the VLSI design flow. What exactly is VLSI stands for? The VLSI stands for very large scale integration. So what are we integrating? When we say integration, what are we integrating? Very large scale means what? Large number of things. What are we integrating? We are integrating transistors basically. There are two major styles of developing the VLSI chips. I mean, there are two major styles of VLSI design flow. One is ASIC. What is the other one? FPGA. ASIC stands for application specific integrated circuits. What is meant by application specific is, I'll give you a simple example. You go to Qualcomm. The Qualcomm, let's say, is developing one mobile phone chip. Let's say Qualcomm has a team who is working on, let's say Qualcomm has a team who are working on developing mobile phone chip from basics, from scratch. This is called as ASIC because whatever design they are working on, whatever this Qualcomm team working on, they are developing on a mobile phone chip, which is called as, since you are targeting this specific application, understand this is important, since you are targeting it to behave like a mobile phone, it is called as ASIC. Do you understand why this term ASIC is used? Because you are developing a thing which will work specifically like one application only. You cannot use this chip, whatever chip that is developed, this cannot be used as a laptop, it cannot be used as a desktop, it cannot be used as a router, it can only be used as a mobile phone. That kind of thing is called as ASIC. Okay. Hardware is developed for specific application only. Example, mobile phone chip. Now what is FPGA? FPGA stands for field programmable gate array. Same hardware in FPGA. The specialty of FPGA is that the same FPGA board can be programmed to behave like different applications. We can, let me just change it. Same FPGA board, the FPGA board can be programmed. FPGA board is the hardware here. The FPGA board can be programmed to behave like different applications, means different electronic devices. It could be that hardware is called as FPGA board. The FPGA board can be programmed to behave like mobile phone, and same can be programmed to behave like a laptop chip also. Those kind of things are called as FPGA. What is FPGA here? You're able to program the FPGA board to behave like a mobile phone, to behave like a laptop or some other device also. Now tell me, if based on this explanation, which one looks better? Does ASIC look better or does FPGA look better? I mean, which flow looks good for us? Can you tell me? It looks, FPGA looks better, right? Because you have more flexibility. You have more flexibility in terms of what you want to develop. Okay. But as we go forward, you will understand that it is the ASIC which industry prefers. Though it looks like, though looks like FPGA is better. FPGA approach is better. Industry prefers ASIC approach, ASIC design flow due to the lower cost of manufacturing. Overall, if you compare, the cost of manufacturing in ASIC design flow is cheaper compared to FPGA. Because of that, the companies prefer using ASIC flow. Let's say if you go to Qualcomm, why do they use ASIC flow for manufacturing of mobile phone chips? Because for them, using ASIC flow to develop the mobile phone chip is cheaper compared to using the FPGA design flow. I hope it is clear to everyone. Now let us compare ASIC versus FPGA flow. I mean, what I'm trying to do is I'm trying to help you understand the very basics of VLSI. I want you to first understand what exactly is an electronic system, what is mean by VLSI, what is mean by embedded system, how do they differ. Then I want you to understand what exactly is ASIC, what exactly is FPGA, and how do they differ. Okay, so that you have a bigger picture of the VLSI domain flow. Okay, now let us understand the difference between ASIC versus FPGA. As you know, ASIC stands for what? Application specific integrated circuit. What does FPGA stand for? The field programmable gate array. First let us understand, let's start off with understanding the cost of ASIC design flow. The cost of ASIC design flow runs into multi-million dollars. Basically in ASIC everything need to start from scratch. I mean, we need to start the entire flow from the scratch. Since we need to do everything from the scratch, we need to spend a lot of money. Multi-million dollars means it runs into, let's say, 8 crore rupees, 10 crore rupees, or upside of that. That is the amount of investment we are talking about. Once, but the good thing is what? Once the flow is working, once the flow is working, the per chip cost is lesser. I mean, manufacturing cost per chip is less. Once you have set up the flow, once you have set up the flow for manufacturing, per chip cost is lesser. Coming to FPGA design flow, the cost, it runs into lakhs of dollars or less. I mean, it is not, it won't be million, it will be lakhs only, lakhs of dollars. Why the cost is less? Because you don't need to start from scratch, we don't need to start from scratch. Hardware is readily available. In case of FPGA board is readily available, right? If it is readily available, you don't need to start from scratch. Because of that, the cost of implementation will be less, the implementing the flow will be cheaper. But per chip cost will be more, because we need to purchase FPGA board for each and every chip. That FPGA board is in general costly. So this is how it works out. Let's say the total cost and the number of units manufactured. I mean, this is the number of units you are manufacturing. This is the cost of manufacturing those units. This graph represents two flows. This line is for FPGA, this line is for ASIC. Generally, when you start, FPGA will start with a lower cost because you just have to purchase the board. Because you have to purchase the board, your cost will be generally lower to start with. Whereas in ASIC, your cost will be high because whether you manufacture one chip or you manufacture multiple chips, your minimum cost will be this much only. Your minimum cost of manufacturing ASIC will be this much. Your minimum cost of manufacturing FPGA will be smaller, lesser compared to ASIC. See, this is minimum. For FPGA, this is this much. Because of that, there is a one point. Till this point, actually FPGA is cheaper. Let's say I want to manufacture 100 chips. For me, FPGA only this much will cost. Let's say it cost me 1000 rupees, 1k. Let's say, okay, let's say this will cost 3k, 3000, because your initial flow, initial cost is very high. That is where we decide if my requirement is to only manufacture this many chips, less than, let's say this number is around, assume 50,000 for example. If my number is less than 50,000, then FPGA is cheaper. If my number is bigger than 50,000, then ASIC is cheaper. You see here, ASIC is on a lower side. ASIC will be cheaper in that case. So depending upon what is the quantity of hardware you want to manufacture, you go with either ASIC flow or FPGA flow. Do you all understand? You can manufacture any hardware using either ASIC flow or FPGA flow. Let's say the mobile phone which I am using can also be manufactured using FPGA flow, but the per chip manufacturing cost is less in ASIC, because once the flow is working, how do they manufacture? They develop it as a wafer, they manufacture on the wafer, they cut these things to get individual chips. So this will become one chip, this will become another chip. So this is what is done in the ASIC. This will be generally cheaper, manufacturing a wafer and cutting the pieces. FPGA flow setup is cheaper, but per chip cost is more. So that this graph explains that. Next, which companies go for ASIC based production? I mean, which companies generally go for ASIC based? That is generally 85% of the companies which manufacture the products for bulk uses. The companies which manufacture products for bulk uses go with ASIC based production. What about FPGA? That is the remaining 15%, remaining 15% of companies which manufacture for limited application. Let us understand what is meant by bulk uses, what is meant by limited uses. It means that if I take a mobile phone, is a mobile phone, is it limited application, limited uses, or bulk usage product? Tell me, what type of device is mobile phone? Is it used in bulk, or is it used only by limited set of people? It is a bulk usage, right? Everyone uses mobile phone. In those cases, since it is bigger, the amount of mobile phones sold will be in millions, like lakhs of phones will be sold. They will go with ASIC flow because at one point my chip cost will be less. If I do the calculation, per chip manufacturing cost in ASIC is cheaper compared to FPGA. But till you hit this point, FPGA is better because you see FPGA line is below ASIC. Next. Now that we have understood the difference between ASIC and FPGA, let us quickly understand the ASIC design flow and the analogy. We will take a simple analogy to understand the ASIC design flow. A very simple analogy, as I said, we will correlate with the real life example. Let's take an example of house construction flow. See, ASIC design flow, if you see, is similar to a house construction flow. So how does house construction flow start with? It starts with the requirements. Requirement is what kind of house do we need? Then once you have the requirement, you go to a house architect. Then to the architect you give the requirements, like what kind of house is the requirement, that you give it to the architect. What architect would give you? What is the output from an architect? Different plans, like architecture diagram, the various plans he will give you. These will become input to the next person, like that. Whatever is the output of the previous stage, that becomes input to the next stage. So then you have a contractor, Mestri, for whom these are the inputs. He will give the building structure, finally constructed. Like that, you go with different people. Now you may ask, why am I talking about house construction? I am here to understand ASIC flow. What I want to tell is this flow and the ASIC flow are very similar. And now, what do I mean by similar is, can I have a painter do the work before architect? Can we involve a painter to do the work before architect? No, right? It has to go through the same flow. ASIC design similarly, ASIC design flow also has a process. The same process need to be followed. You cannot change the order, you cannot move this here, you cannot move this here, you cannot, that cannot be done. That flow is fixed. Now let us understand the flow that is involved in ASIC design flow. You see, there are many people involved: architect, contractor, plumber, electrician. There are so many people involved. Similarly, ASIC design flow is not done by one person. It is not done by one person. It is multiple people who work into ASIC design flow. Now, ASIC design flow consists of 15 steps, around 15 steps, divided into two major categories. Can someone tell me what are the two major categories in ASIC design flow? ASIC flow has two domains called as front-end domain, back-end domain. See, entire ASIC flow can be divided into two categories: front-end domain, back-end domain. Front-end domain is about developing the Verilog or VHDL code, verifying that code, understand the design, develop the design Verilog code, and verify the Verilog code. The everything after that, once you have verified the Verilog code, everything that starts after that is called as backend domain. That is the remaining flow. So now let us understand what all steps are involved in the front end domain flow. You have initially, it starts with design requirement, then you have architecture, then you have RTL design, then you do the RTL integration, then we do RTL functional verification. So where do we use the term RTL? Can someone tell me? Then we use DFT at the Verilog RTL level. Then we have, so that is about front end domain flow, what all aspects that are present in the front end domain. Then we have back end domain where we use synthesis, where what is synthesis called as? Converting Verilog RTL code into, RTL stands for what? Register transfer level code, into gate level is called as synthesis. Synthesis is an important point where you move from front end to back end domain. Synthesis is the transition point from where you go to back end domain. Then you do the DFT, design for testability at the gate level. Then once it is done, then you do physical design, which involves floor plan, placement, power plan, clock tree synthesis, many things you do as part of the physical design. So what exactly is physical design is, once you have done the synthesis, you have got different blocks, okay, called as macros and standard cells. Okay, arranging them in a right manner into your chip area and connecting them properly is all consists of physical design. Though it looks easy, you may see what is there in this, keeping this block here, this block here. You have crores of such blocks. I mean, hundreds or thousands, even standard cells will be in lakhs. So that's what makes physical design very challenging. Once the physical design is done, you have static timing analysis. So after static timing analysis, we have custom layout. We do custom layout where the gates are implemented at transistor level. See, gates finally need to be converted to transistor, right? That will be done as part of the custom layout. Then we have physical verification. Basically, here you do the basic physical level rule checking, whether all the metal layers are kept properly, whether the uh, what do you say, the metal to metal distance is proper. I mean, let me not get into deep of it, just understand that some basic rules they will check. I'll give you a simple analogy. You take electrical line transmission. See, there are poles, right, which will carry electrical lines from one point to other point. So here, if I have to refer what exactly is physical verification, is checking whether the thickness of wires is proper, checking whether the distance between one electrical wire to other electrical wire, is it at least 1 feet difference is there. Those are the kind of things we are calling as physical verification checks. This is in terms of electrical transmission, voltage current transmission. I am talking from a chip perspective. Then you have something called as, once you have done physical verification, we do something called as GDS2 extraction. This is called as graphic design stream, design system, graphical design system. Okay, this, what exactly is GDS2 is, GDS2 will tell, GDS2 is graphic design system. It will give the design, I mean the entire chip level, I mean silicon level description of the chip. What exactly is silicon level description? Let's try to understand. Basically, if this is my silicon, it will tell, here there will be a polysilicon. Here you need to do the p doping, here you need to do n doping, how much depth you have to do, what level of doping you need to do, and where you need to deposit the metal, where the metal should be deposited, where the gate should come, where the drain should come, where the voltage line should come. That description they will give in a graphical format. They will tell, it's like a three dimensional description of the entire chip. So this you give it as a input to the foundry. So GDS2 is given as input to the foundry. Foundry could be like TSMC. They will manufacture the chip. Once the chip is manufactured, we do something called as post silicon validation. Whether the chip is working fine or not, we check. That is called as post silicon validation. Once the post silicon validation is done, we go for packaging. So once you do packaging, you have the final electronic product. So the mobile phone that you are using right now, it went through all this process. Can you read through these steps once again? So the whole ASIC flow can be divided into two categories. One is front-end domain, one is back-end domain. Front-end domain is more about working at Verilog level, understand the design, understand the architecture, implement the design, integrate the design subblocks, then do the verification. Once the verification is done, you need to manufacture into chip, right? When you go to mobile phone, will they sell the Verilog code? Do they sell Verilog code? No, right? They will sell you this. This process of bringing this Verilog RTL into this format is called as backend domain. The entire flow is involved in that. Okay, now let us understand what are the challenges in the VLSI design flow. I mean, some of the challenges, this session is too short to discuss about entire list of challenges. I'll at very top level, we'll talk about some of the challenges. See, VLSI design is driven by three factors. We can call those three factors as three P's, PPP. What are these three P's? The first one stands for performance. First P stands for performance. Second P stands for power. The third one stands for price. The basic guideline is in any design flow, we can only get best of the two of these things best. Okay, in any design flow, in any VLSI flow, design flow, we can only get two best of the uh, two best out of these three. You can't get all best, like you can't have best performance, best power consumption, and best price. Somewhere you have to compromise. That is where only two out of these can be best. Now, what is performance? Performance is basically how do you get by you get the performance by increasing the frequency of operation. You generally get the performance by increasing the operation. What exactly means by performance? How quickly a given job can be done. So to do that, you need to increase the frequency of operation. But as you increase the operation, what is the challenge you face? As you increase the frequency, you face some challenges. One of the challenges you face is the timing closure. Means there is something called as setup time analysis and hold time analysis. As we as we increase the frequency, it gets difficult to do setup time closure. As we increase frequency, it gets difficult to do the setup time closure. Now, what exactly setup time? If you understand the basics of D flip flop, there will be something called as a setup time and there will be something called as hold time. Okay, that is one challenge we face. Timing closure is one challenge. Now, as you increase the frequency, since you are doing high performance, that will result in an increased power consumption. The increased frequency will give increased power consumption. So these are the two challenges which limits the frequency of operation. These are the two challenges that we face in the related to performance. Because of that, we are not able to increase the frequency beyond a level. The second factor is power consumption. See, what is the power consumption? What exactly is power consumption? There are two types of power consumption. One is static power consumption, one is dynamic power consumption. The challenge related to power consumption is, as you know, as frequency is increased, I told you, as the performance gets increased, it always results in increased power consumption. It always results in increased power consumption. Leakage, and also the other challenge we face related to power is leakage due to short channel effects in the lower technology nodes. If you see 3 nanometer technology node, 5 nanometer technology nodes, you will come across the terminology called as short channel effects. They will result in leakage, which increases the power consumption. So these are the challenges you face with respect to power consumption. The third factor is price. How do you achieve reduced price? By reducing the die area. Increase, basically make the chip smaller. So you will be able to manufacture more chips in the same silicon. The challenges we face is the yield. As you reduce the die area, to reduce die area, we move to lower technology nodes. Reducing the die area by moving to lower technology nodes. But the problem is, as you move to lower technology nodes, the manufacturing defects becomes more and more prominent. Because of that, the yield gets reduced. Uh, Yield reduced gets reduced yield due to increased manufacturing defects. I mean, because as you move to low technology nodes, manufacturing defects will increase, which will reduce the yield. Yield means, what exactly yield means is the number of good chips per 100, per every 100 chips manufactured. Simple. Let's say you have manufactured 100 chips. Out of them, 82 are good. So your yield is 82%. That means what? 18 chips are bad. So your yield will be 82%. So these are the challenges which we face in the VLSI design flow. Next. So this is a very brief about challenges. Let's not get into it. I mean, why this is important? This could be the some of the research areas, some of the areas where which you can explore, because you always, as a research person, you try to solve the challenges, right? What challenges are involved in the flow? So you can focus on performance, you can focus on power, you can also focus on how the cost can be reduced. Now, let us move to the next part of the lecture, where we will talk about VLSI front-end domain flow. Because I told you that VLSI flow consists of two aspects. One is the front-end domain, one is the back-end domain. Now, let us talk about the VLSI front-end domain flow. Front-end domain, VLSI front-end domain is similar to a software flow. In a software flow, like what does a software engineer do? They have a software. The architect will give the software architecture. The developer will be there who will develop the software. Then you have a tester. Automation testing or manual testing is used to check the software behavior. So that is what is the skill set required by a software engineer? He should be good with C++ or Java, these languages. He should be good at reading software design specifications, and read the software design specification, develop the algorithm, and implement these algorithms using C++, or Java. Similar to this, even a VLSI front-end domain engineer needs a similar skill set. Like you need C language, here you need Verilog, here you need System Verilog, you need UVM. Like a software engineer, C++, Java, a VLSI front-end domain engineer needs Verilog, System Verilog, UVM. See, I'm not talking about back-end domain. I'm not talking about physical design. I'm not talking about DFT. I'm not talking about layout. I'm only talking about front-end domain engineer needs to know these languages. Other than that, you should be good at reading hardware design specifications, which will talk about how the hardware works. Then we should be able to implement different requirements using the various protocols. Like the protocols, you mean USB, PCI Express, DDR, SPI, these kind of protocols. You see, software doesn't involve any backend flow. So what is mean by that? You don't manufacture a software. You develop a software and you install it into a system. Okay. What is backend flow? When I say backend flow, what exactly is it? Process of converting the code into a chip is called as backend flow. Generally, chips don't have any concept of patch. Means once the chip has a bug issue, the entire flow is gone. You have to redo the entire flow. In software, that is not true. In software, if some software has a bug, you can just fix the bug and release a new version of the software. In hardware, you don't have anything. Let's say I have a mobile phone. Inside the mobile phone, there is a chip, there is some fault. I cannot fix it and release this mobile phone as a new version. I have to go through the entire flow again. That is what I mean by chips don't have any concept of patch. But whereas software has patches, you keep getting patches of software 1.2, 1.3, new patches keep coming. Now, let us understand the pre-synthesis flow. What is involved in the pre-synthesis flow? That is VLSI front-end domain flow. What is involved there? Design requirements, architecture, RTL design, RTL integration, and functional verification. Similar to that, backend domain flow involves various steps like synthesis, gate level simulation, DFT, physical design, static timing analysis, custom layout, physical verification, fabrication, and finally you have post silicon validation. Next, now that we have understood what exactly is a VLSI design flow, we understood that the VLSI design flow consists of majorly two aspects. One is the front end domain, one is the back end domain. Now let us understand different job roles in the VLSI domain flow, design flow. There are again two domains, front end domain, back end domain. In front end domain, the person or the team which works on design requirements, they collect the design requirements, is the marketing team. The person who works on architecture is called as design architect. The person who works on RTL coding, I mean Verilog RTL coding, is called as RTL design engineer. The person who works on RTL integration is called as RTL integration engineer. The person who works on RTL verification, RTL functional verification, is called as functional verification engineer. In fact, this also should be RTL functional verification. They are called as functional verification engineers. And the person who works on DFT is the DFT engineer, as I said. The person who works on synthesis is synthesis engineer. Like that, you can see that for every job role, for every domain, there is one specific job role. This is what makes the things difficult for us. What do you mean by that? It makes difficult with so many job roles. How do you choose which domain is suitable for you? I mean, whether you should you become a design engineer, should you become a RTL integration engineer, should you become a DFT engineer or physical design engineer or post silicon validation engineer? So many things are there. How do you decide that? Okay. That is where you need to understand what is your primary area of interest. Do you want to get into front end domain? Do you want to get into back end domain? That is the first step in the decision making. See, in software, you don't have this confusion. Software job roles are straightforward, easy, simple. What is it? That software architect, then you have software developer, then you have software tester. You can't become an architect because just to start with a career, you can't become an architect. So you can either become a developer or you can become a tester. So there is no confusion there, because in software there are only two job roles which you can target. Either you can become a developer, you can become a tester. Tester means what? Manual testing, test automation, QVP test, automated testing. There are various things are there. In the VLSI, that is in the hardware, there are different job roles. You can become a RTL engineer, integration engineer, functional verification engineer, formal verification, physical design. STA, layout. So many different job roles are there. So typically this is how the distribution will be. If you have a team of 50 people, let's assume you are working on a mobile SoC project. If the team is of size 50, around 25 to 30 will be into front end domain. Around 20 to 25, a small percent less, around 10% less in backend domain. Typically, architect will be only one. You don't want multiple people to do architecture. There will be only one architect. Then you have design team, which has got around 4 to 6 people. Then you have got functional verification team, which has got around 15 to 20 people. You see, lot of people work in, for 30 to 40% of this team works in functional verification. Other than that, you have backend domain, which has around 20 to 25 people. In that, DFT will be having 2 to 5 people, physical design around 10 to 15. You can see this is around 20 to 30%. So two major domains where a lot of people work is functional verification and physical design. Then you have static timing analysis, layout. Now, if you ask me, does it mean that all jobs will be there in this only? Answer is no, uh, because there are other roles where people are also involved. Only thing is, relatively, these positions will be less compared to functional verification and physical design. Then you may think, if I have to join the training, if at all you have to join a training, I'll join either this or this. Not like that. Even though, see, even though this has less jobs, the number of people who undergo training will be less. Here, only 10 to 15 people will join. In functional verification, around 50 to 60 people will join. So automatically everything is adjusted. So don't think that if I join functional verification, I will have lot of jobs. In DFT also, you join, since less roles are there, less people will undergo training. Same thing with other domains also. I hope you got an idea of how a team gets distributed. It is very rough estimate. Okay, don't think that where is 15 people, where is 20 people. It is a range. I mean, this could be the number of people who work into different domains in the project flow. Next. Now, let us understand, as a VLS engineer, let's say you are pursuing your BTech or Masters, what is the skill set that you require to get into the industry, to get into a VLSI job? As a VLS engineer, the common skill set that you need will be, you should be, first, let's to start with, you should be very good with digital design. You should have very strong digital design fundamentals. Then you should be good with Linux operating system. Then you should have a basic scripting language knowledge, either Perl, Python, or TCL. Other than that, you should be comfortable with working on text editors, like I mean GVim text editor, uh, Notepad plus plus text editor. You should be good with that. Other than that, uh, some semiconductor fundamentals should be good. Then, as a front end domain, let's say you want to get into front end domain, that is the RTL design, RTL integration, and RTL verification. You want to get into that job role. What is the skill set that you require? You should be good with standard protocols like on chip protocols, peripheral protocols. There are different types of protocols you should be good with. Other than that, you should have a good programming expertise. To become a front end domain engineer, your programming skills should be good, like learning hardware design description languages like Verilog and VHDL, learning hardware verification languages, you should be comfortable. Other than that, you should have a good debugging expertise. Like if something fails, why is it failing? Those kind of debug expertise should be there. Like debugging simulation failures, tracing the design issues using the tools, analyzing the failing test logs. So all that skill set, this entire skill set you require to get into front end domain job role. You see, majorly you should be inclined towards programming and towards learning the protocols and towards debugging. I mean, why something is failing? What is the reason? What is the code I need to fix to make it work? That kind of approach skill set is what a front-end domain engineer needs. Now, talking about back-end domain, what is the skill set that is required? You should be a backend domain engineer should be good with the VLSI technology concepts, like what is meant by current, what is voltage, what is rise time, what is fall time, what is propagation delay. Different things will be there. You should also be good with semiconductor fundamentals, and also you need a good tool expertise. See, in backend domain, a lot of EDA tools, or you can call EDA softwares, electronic design automation tools, softwares will be used in the flow implementation, like EDA tools, ICC2, Prime Time, Design Compiler, Star RC, various tools you should be comfortable with. Then you should have a good TCL scripting expertise. Then you should have understanding of IC fabrication. Then device and semiconductor fundamentals. These are all the skill set you require as a backend domain engineer. Now let us talk about with all these domains, VLSI design flow, front end domain, back end domain. How do we choose a right domain? Okay. So first thing you should do is you choose either front end or back end domain based on skill set interesting for you. If you find programming to be interesting, you go with front end domain. Otherwise, if you don't like programming at all, you go with back end domain. You see, job opportunities will be there for every domain. You should not think that only front end has opportunities or only back end has the opportunities. Every domain has the opportunity. Do not come with the mindset that I can't do programming at all. I mean, you may not have done, but you should have a you should be open to learning the programming also. Next, how to prepare for the job. How should I start my preparation? I mean, let's say you are in BTech third year, you want to get into the industry after your BTech completion. How can you do that? You should spend at least a dedicated 6 months time. Need not be continuous, it can be distributed over multiple semesters. Divide your preparation into multiple stages, like Verilog is one stage, system Verilog, UVM. Then other aspects like VLSI design flow, digital design, CMOS basics. Then the fifth stage will be Linux and scripting. You should learn all those things, and all these languages should be learned more emphasis on practical aspects than theoretical. You should give more emphasis on the practical aspects, how it gets used, something you need to question for everything you learn. I mean, you should question for everything you learn. Next, where to find opportunities? Like, how do you find the opportunities? Mostly you get it in LinkedIn. You can always send it to career email of the various companies. Next, why to choose a VLSI career? I mean, what should be motivating factor? One is work satisfaction, right? Because that is what you are learning as an electronics engineer, ECE or triple engineer. You are learning mostly the things related to electronics. So by getting into VLSI, you will be doing a work which is closer to what you are learning now. And the career opportunities. See, VLSI has almost 50 plus product companies and 100 plus service based companies. So you will get opportunities, and this is only open to, these companies are only open to electronic students. They don't hire IT, they don't hire MCA student, BSc students. There is no significant requirement for reskilling once you learn in once you get into job. See, typically what happens in software, every 3 4 years things keep changing. See, now it is not very much relevant. Thus, you need to keep learning new skill set, that is like reskilling. Whereas in VLSI, because it is about chip manufacturing won't change drastically, right? You don't need to reskill. Once you get into job, what you do on the job you learn there itself. And generally VLSI domain is a well paid job. A 5 years experience engineer in VLSI earns anywhere between around 15 to 25 lakhs per annum. These are significantly high paid jobs in VLSI domain. Okay. So this is a very brief about the VLSI career, VLSI challenges in VLSI domain and the opportunities. Now, if you have any questions, I can answer those. Please feel free to ask any questions that you have related to the VLSI domain. Uh, Hello, madam, Kusumadara, madam. Any questions your team having?
Sir, as a basic learner, I'm Savita, sir, from KVG College of Engineering.
Yes, madam.
As a basic learner, these students are basic learners. Which you do you prefer, sir, whether front end or back end? Because they have the foundation knowledge of something like digital electronics, semiconductors, and apart from that, related to chip aspect and manufacturing layout, something and all, they are not having that much idea right now. And the basics of very basics of very long, they are having these knowledges. So whether to choose front end as a basic learner or back end as a basic learner, is there any,
Uh,
which one is better to choose, sir?
Madam, it would be good to start with Verilog, madam. I mean, see,
Uh,
first of all, they need to start learning Verilog language.
okay,
If they
basics
find
of
it
very long.
interesting, if they find it
Yeah,
interesting, because it will give them exposure to the basic programming skill set. If they
yeah.
find it interesting, then they can choose front end domain as the career option. If they don't
Okay,
like Verilog language, I mean the programming that is coding that is involved in Verilog, then they can move to backend domain.
okay, sir. So that's what if start from top, at least they will get a clear picture of entire design flow or used in a VLSI domain. So better to choose front end. You mean to say, no, sir?
Yes, madam. I mean, I won't say better to choose front end. I am only
Uh,
telling start learning Verilog language. It is only
Language
one part
start.
of the flow. Once you learn it, if you like the programming, you continue with front end domain. Otherwise, if you don't like it, you don't enjoy coding, then you choose back end domain. Knowing Verilog is good for everyone, even a back end engineer. Knowing Verilog language is good. Any other questions, madam?
As part of technical thing, I don't have any questions, sir, now.
Okay, madam. Someone has asked a question by name Vaibhav. So, since FPGA is a multitasking one, why don't mobile manufacturer use it rather than ASIC? See, the answer for that question is basically the cost of manufacturing a this thing is much higher compared to cost of manufacturing a FPGA. I'll give you one example. I have made one notes. So through that notes, I'll explain. To take this example, let's just go through one table. The ASIC per chip manufacturing cost is $15 generally. Assume flow setup cost is $1 million. Because in ASIC, what happens is once you manufacture the wafer, there will be hundreds of chips on this one wafer. Each one is a chip that goes into your mobile phone. This one is a chip that goes into your mobile. This one is a chip. Everything is a chip that goes into your mobile phone. But the initial flow cost is very high. In FPGA, the cost of manufacturing per chip is costly, $50. Flow setup cost is $1 lakh only. Now, to manufacture 1,000 chips, ASIC cost will be 1 million because initial investment is 1 million plus 1,000 into 15. 1,000 why? Because you are manufacturing 1,000 chips. Your overall cost will be this much. Per chip, average cost per chip, per chip, average cost per chip will be $1,015. If you divide this with 1,000, you get $1,015. Whereas you take FPGA cost, your initial investment is 1 lakh plus 1,000 into 50, it will come to 150,000. Average cost per chip will be how much? Average cost per chip will be $150. See, if you are manufacturing only 1,000 chips, FPGA is better. See, for manufacturing in smaller quantity, FPGA is better option. But let's say now we are manufacturing 1,000 chips, 1 lakh chips. There is another requirement where we have to manufacture 1 lakh chips. So the ASIC cost will be what? 1 million plus 1 lakh into 15, which will come to 2.5 millions on average cost per chip. See, what will be the average cost per chip here? It will be $25. In this case, in the FPGA, since your initial investment is 1 lakh and per chip cost is 50, it will overall come to $5.1 million. So the average cost per chip, if you divide this with 1 lakh, it will come to $51. See, for bulk production, FPGA ASIC is, so there will be a break-even point where anything below this ASIC is FPGA is better. Anything above if ASIC is better. So it depends upon this. What is the cost of per chip manufacturing? That all factors will decide it. Vaibhav, I hope it is clear to you. What is the difference between ASIC and FPGA cost? Why companies prefer ASIC flow for manufacturing the mobile phone chips? Is that clear? Okay. Any other questions you have? Um, okay, if you don't have any questions, we can end the session. Thank you everyone for attending, taking out time and attending this demo session. If you have any further queries, you can reach out to us.
Okay.
Okay. So how can you reach out? You can just WhatsApp us on this number 194191 with your queries. Like you can also go for career guidance.
Okay.
How can you, what can you do uh, as part of your BTech? Let's say you're pursuing your BTech, you don't need to wait for BTech completion to start learning the VLSI. You can start learning VLSI subject while you are pursuing your BTech, and that will be a better option because instead of spending 6 months, 1 year time after the BTech completion, it will be a good idea to pursue VLSI subject while you are pursuing BTech. My only suggestion is do not do entire 6 months in one semester. Divide one minor course like Verilog in fifth semester, maybe the Verilog projects in sixth semester, system Verilog
Okay.
in seventh semester, UVM or industry project in eighth semester. Like that, you could distribute your learning. This is how you can uh, focus. Let's say you are already in seventh semester, you shift it. See, the good thing is what? If you learn some basic things, you don't have to spend the same time, right, when you pass out of the college. That is how you can work on it. Okay. Any questions you have before we end the session? Okay.
Thank you very
Thank
much,
you.
sir.
Okay. Sure, madam. Thank you,
Thank you.
everyone.
Thank you very much, sir, for giving a very basic idea of which one to choose for to our student. Given us a very much basic foundation knowledge about which domain to use very nice manner. Thank you, sir. Thank you very much, sir. Uh,
Sure, madam. Thank you so much for your feedback.
Can you
Yeah.
I
Yeah, madam.
contact like Harsha sir?
Yes, madam. You can
Is
speak to Harsha further.
Harsha? Okay.
Thank you, madam.
Is
Thank you, everyone. We'll end the session here.
all right. Sir.